Picture the night sky not as a quiet tapestry of distant pinpricks, but as a roaring arena of cosmic titans, each one a furnace of unimaginable power. Among them, some stars don't just shine, they dominate, bending the very fabric of space and time around them with their sheer might. What if, just for a moment, our humble sun vanished, and in its place blazed one of these stellar behemoths? The gentle warmth we know would vanish, replaced by a force so intense it could rewrite the rules of our solar system in an instant. This isn't science fiction, it's the reality of the universe's most powerful stars, and today we're embarking on a journey to meet them. Think of this as a cosmic safari, where instead of lions and elephants, we're tracking down celestial giants, stars so colossal, so ferociously energetic, they make our sun look like a flickering candle in comparison. Some of these stars could swallow entire planets without a second thought. Others unleash storms of radiation so fierce they sculpt entire nebulas like cosmic artists. And a few, they're ticking time bombs, destined to explode in supernovas so bright they'd outshine entire galaxies for weeks. These aren't just stars, they're the universe's ultimate power players, and their stories are written in light, fire, and gravity itself. But why do these 30 stars stand above the rest? It's not just about size or brightness, it's about the raw, unfiltered influence they wield. Some are so massive they warp space-time, creating gravitational whirlpools that trap even light. Others are ancient relics from the dawn of the universe, burning with secrets about how everything began. And then there are the vampire stars that steal life from their neighbors, growing stronger as they feed. This isn't just a list, it's a front row seat to the most spectacular shows the cosmos has to offer. So buckle up, by the time we're done, you'll never look at the night sky the same way again. If our sun were a marble, UY Scuti would be a hot air balloon so gigantic it could swallow the entire inner solar system without breaking a sweat. Nestled in the Scutum constellation over 9,000 light-years away, this crimson leviathan isn't just big, it redefines the word. With a radius stretching 1,700 times wider than our sun, it's the undisputed heavyweight champion of stellar size. Picture this: if UY Scuti took the sun's place, its searing surface would extend beyond Jupiter's orbit, engulfing Saturn and everything in between. Even light, racing at 670 million miles per hour, would take over 7 hours to travel from its core to its faint, wispy outer layers. But UY Scuti isn't just a static spectacle, it's a pulsing, unstable titan. Its brightness flickers unpredictably, dimming and flaring like a cosmic heartbeat. This happens because it's in the final, violent throes of its life cycle, fusing heavier elements in a desperate battle against gravity. The star's outer layers are so loosely bound that they billow into space, forming a vast, shimmering cloak of gas and dust. Astronomers call this a hypergiant phase, a brief and fiery prelude to a supernova explosion so colossal it could outshine our entire galaxy for weeks. What makes UY Scuti even more fascinating is its sheer fragility. Despite its mind-bending scale, it's less dense than Earth's atmosphere at sea level. If you could stand on its surface, which you couldn't because it's not solid, you'd weigh almost nothing, floating in a hazy inferno of ionized gas. And here's the twist: we're likely underestimating its true size. The star's distance and dusty shroud make precise measurements a nightmare, meaning UY Scuti might be even larger than we think. One thing's certain: when this star finally detonates, it won't just fade away, it'll rewrite the cosmic landscape around it, scattering the building blocks of future stars and planets across the void. Just when we thought UY Scuti had secured its place as the universe's largest known star, along comes Stephenson 218, a red supergiant so vast it makes even that colossal titan seem almost modest by comparison. Lurking within the dense Stephenson 2 star cluster nearly 20,000 light-years away, This mammoth star wasn't even recognized for what it truly was until recent infrared telescopes pierced through the cosmic dust, hiding its staggering dimensions. Initial measurements suggest a radius stretching 2,150 times wider than our Sun, so immense that, if placed at the center of our solar system, its outer layers would brush against the orbit of Saturn. But what's truly mind-bending about Stephenson 218 isn't just its size, it's the paradox of its nature. While its surface simmers at a cool 3,200 Kelvin, giving it that deep crimson glow, it blazes with a luminosity 440,000 times brighter than our Sun. How does something so relatively cold pump out such absurd amounts of energy? The answer lies in sheer scale. Even though each square inch of its surface is less intense than the Sun's, Stephenson 218 has so much surface area that its total output becomes mind-numbing. It's like comparing a bonfire to a million matches spread across a continent, individually tame, collectively unstoppable. This star also offers a fascinating glimpse into stellar neighborhoods. Nestled in a bustling cluster packed with other supergiants, Stephenson 218 isn't a solitary behemoth but part of a cosmic dynasty. Infrared observations reveal how these stars interact, their fierce radiation carving cavities in the surrounding nebula like giants wading through fog. Yet even among its peers, Stephenson 218 stands out not just for its size but for its instability. Like UY Scuti, it's shedding mass at a furious rate, shrouding itself in a glowing cocoon of ejected gas that complicates measurements and hints at an explosive fate. The real intrigue, we might still be underestimating it. The same dust that once hid Stephenson 218 could still be obscuring its full extent, meaning future telescopes could reveal it's even larger. One thing's certain, whether it ultimately claims the size crown or not, this star forces us to rethink what's possible in the universe. It's a reminder that beyond our calm corner of space, existence operates on a scale so grand it bends comprehension, where stars don't just shine, they rewrite the rules. VY Canis Majoris isn't just a star, it's a cosmic catastrophe in slow motion. Located 3,800 light-years away in the constellation Canis Major, this crimson hypergiant is so unstable it's literally tearing itself apart, coughing up colossal chunks of its own atmosphere into space. Every year, it ejects 30 times Earth's mass in a desperate, fiery struggle against gravity, enough material to form an entire planet. If our Sun were losing mass at this rate, it would vanish completely in just 100,000 years. But VY Canis Majoris is no ordinary star. It's a ticking time bomb, and the countdown to its inevitable supernova has already begun. What makes this star so mesmerizing isn't just its impending doom, it's the breathtaking spectacle it's creating right now. Surrounding the hypergiant is an intricate nebula, a glowing web of gas and dust stretching over half a light-year wide. This isn't some peaceful cosmic cloud. It's the aftermath of titanic stellar tantrums, where violent eruptions have sculpted vast arcs and filaments that resemble celestial brushstrokes. The nebula glows in vivid reds and oranges, illuminated by the dying star's intense radiation, a portrait of destruction painted on an interstellar canvas. The story of VY Canis Majoris reads like a 19th-century astronomical thriller. First catalogued in 1825 as a faint variable star, its true nature remained hidden for decades. Early astronomers saw only a dim red speck, unaware they were witnessing one of the largest stars ever discovered. It wasn't until modern telescopes peered through the dust that we grasped its staggering scale, over 1,400 times wider than the Sun, so vast that light would take 8 hours to circle it once. But size isn't its only claim to fame. VY Canis Majoris is a laboratory for stellar death, offering clues about how the most massive stars meet their end. Unlike smaller stars that fade quietly, hypergiants like this one go out with a bang, a supernova so powerful it could outshine its host galaxy for weeks. When that happens, the shockwave will trigger new star formation, scattering heavy elements like gold and uranium across space. Every time you look at a piece of jewelry, you're holding remnants of a star that died just like VY Canis Majoris eventually will. The real mystery, we don't know when the explosion will come. It could be next year, or it could be 100,000 years from now. But one thing's certain, when this behemoth finally goes supernova, it won't just be the end of a star. It'll be a dazzling cosmic rebirth, forging the building blocks of future worlds and rewriting the story of its corner of the galaxy. Until then, we'll keep watching, learning from every violent gasp and shudder of this celestial titan. Westerlund 126 doesn't just challenge our understanding of stars, it defies it. Hidden within the Westerlund 1 superstar cluster 16,000 light-years away, this celestial enigma has sparked heated debates among astronomers for decades. Is it a hypergiant stretching 2,550 times wider than our Sun, or a more modest 1,500 solar radii? The confusion stems from its bizarre behavior. A star that flickers between spectral types like a cosmic chameleon, sometimes appearing as a cool red supergiant, other times showing the fiercer signature of a hotter yellow hypergiant. Hubble's sharp eye has revealed why this star is so hard to pin down. Nestled in a glittering metropolis of young, massive stars, some shining millions of times brighter than our Sun, Westerlund 126 is literally cloaked in its own drama. Towering plumes of dust and gas swirl around it, ejected during violent outbursts that have left astronomers questioning whether we're seeing the star itself or just the echoes of its tantrums. These aren't gentle stellar winds, they're hurricane-force ejections powerful enough to sculpt entire nebulas with filaments stretching light-years into space. What makes this star truly extraordinary is its cosmic zip code. Westerlund 1 is no ordinary cluster. It's a stellar nursery brimming with rare, short-lived giants, packed so tightly that our entire solar system could fit between some of them. In this stellar mosh pit, Westerlund 126 stands out not just for its size, but for its sheer unpredictability. While most hypergiants pulse rhythmically like cosmic heartbeats, this one flares erratically, as if teetering on the edge of stability. Some theorists suggest we might be witnessing a star in unprecedented transition, perhaps flipping between evolutionary states as it consumes the last of its nuclear fuel. The most tantalizing clue lies in its light. Unlike typical red supergiants that glow steadily, Westerlund 126's spectrum shows bizarre absorption lines, chemical fingerprints hinting at layers of its atmosphere sloughing off at different rates. It's as if the star is shedding its skin in uneven patches, creating a patchwork of temperatures and densities that flummox our telescopes. This could explain why size estimates vary wildly. We might be seeing not a single surface, but multiple shells of ejected material masquerading as the star's edge. Hubble's breathtaking images add another layer to the mystery. The cluster surrounding Westerlund 126 looks less like a peaceful starfield and more like a cosmic battlefield, with shockwaves from colliding stellar winds carving intricate bubbles in the nebula. Young, blue-white stars, each destined to explode within a few million years, outshine their smaller siblings, while dark lanes of dust twist through the scene like celestial brushstrokes. In this violent nursery, Westerlund 126 looms like an elder statesman, its fate intertwined with its neighbors. When it finally explodes, the resulting supernova could trigger chain reactions across the cluster, birthing new stars even as it destroys. Perhaps the most humbling realization, we're seeing this star as it existed 16,000 years ago, around the time humans first domesticated wolves. By now, it may have already met its fiery end, leaving behind a neutron star or black hole we won't detect for millennia. Westerlund 126 reminds us that the universe doesn't exist for our convenience. Its greatest spectacles unfold on timescales that dwarf human history, in corners of space where the rules we know bend and twist beyond recognition. RW Cephei doesn't just shine, it breathes. Imagine a colossal, writhing sphere of plasma so vast that if it replaced our Sun, its outer layers would brush past Jupiter's orbit. But unlike the steady glow of familiar stars, this crimson behemoth swells and shrinks like a cosmic lung, its radius oscillating between 1,000 and 1,600 times wider than the Sun over years-long cycles. Located 3,500 light-years away in the constellation Cepheus, RW Cephei isn't just a star. It's a pulsating laboratory, offering scientists a front-row seat to the chaotic final acts of a hypergiant's life. What makes these rhythmic expansions so mesmerizing isn't just their scale. It's what they reveal about stellar mortality. As RW Cephei inhales, heating and compressing its core, it fuses heavier elements in a desperate bid to stave off collapse. When it exhales, its outer layers balloon outward, cooling to a deep ruby hue and shedding enough material to seed future planets. Each pulse sends shockwaves through its atmosphere, triggering fireworks of nuclear reactions that astronomers can detect across interstellar space. These aren't gentle vibrations, they're seismic stellar quakes, so powerful they alter the star's brightness by nearly 50%. Artist renderings capture RW Cephei's haunting beauty, a smoldering ember suspended in a velvet void, its light filtered through veils of cosmic dust that glow like scattered candlelight. The dust isn't just backdrop, it's the star's own discarded skin, ejected during violent eruptions that have left it shrouded in a nebula of its own making. Infrared telescopes peer through this haze to reveal a surface so turbulent it resembles a boiling ocean, with convection cells larger than our solar system churning beneath an atmosphere thin enough to see through. But RW Cephei's true value lies in its contradictions. Most pulsating stars follow predictable rhythms like clockwork. This hypergiant, though, stutters and staggers, its pulses erratic, its brightness flickering unpredictably. Astronomers realize these aren't just random spasms. They're symptoms of a star teetering on the edge of stability, its core running out of fuel while its outer layers rebel against gravity's grip. By studying these death throes, scientists have uncovered clues about how the universe's mightiest stars recycle themselves. The heavy elements forged in RW Cephei's heart, carbon, oxygen, iron, will one day blast into space, seeding nebulae where new stars and planets will rise from the ashes. The most humbling thought, RW Cephei's light reaching us today began its journey when humans were inventing the wheel. By now, this stellar titan may have already met its fiery end, collapsing into a neutron star or black hole we won't detect for millennia. Until then, its flickering glow remains a cosmic lighthouse, guiding us through the turbulent seas of hypergiant evolution, a reminder that even the universe's grandest monsters are, in the end, fleeting. KY Cygni doesn't just hide in the shadows, it wraps itself in them. Tucked away 5,300 light-years from Earth in the constellation Cygnus, this stellar recluse is veiled by a self-made cocoon of dust so thick that visible light can't pierce it. What slips through the haze, though, reveals a monster, a pulsating hypergiant with a radius stretching 1,650 times wider than our Sun. If placed at the center of our solar system, its outer layers would stretch beyond Jupiter's orbit, yet we'd barely see its glow, just a dim ember peeking through a storm of its own making. The real magic happens in the infrared. Here, KY Cygni transforms from a faint smudge into a blazing titan, radiating 500,000 times more energy than the Sun. Its dusty cloak, forged from atoms the star has violently ejected, glows warm against the cosmic backdrop like a street lamp seen through fog. But this isn't just any dust, it's laced with water vapor and hydroxyl molecules, creating natural lasers astronomers call masers. These beams of amplified light ripple outward, mapping the star's turbulent atmosphere in radio waves. Imagine a lighthouse, but instead of light, it's broadcasting its distress in microwaves, screaming its existence across the galaxy. What sets NML Cygni apart isn't just its disguise, it's the sheer violence of its self-destruction. Every year, this star sheds enough material to build 30 Earths, a rate dwarfing even VY Canis Majoris. Spectroscopic studies reveal cavernous winds tearing through its outer layers at nearly 20 miles per second, carrying away whole suns' worth of matter over its lifetime. These aren't gentle breezes, they're tsunamis of gas, sculpting spiral plumes that stretch light years into space. Infrared images capture these ejecta in breathtaking detail, swirls of silicate and carbon dust glowing like molten glass, twisted by magnetic fields into intricate tendrils. The star's OH/IR signature, a telltale radio emission from hydroxyl molecules, betrays its advanced age. Like a cosmic fingerprint, this signal reveals NML Cygni as one of the rare OH/IR stars, a class of elderly hypergiants cocooned in their own debris. These molecules form when ultraviolet light splits water vapor, then recombines into hydroxyl in the cooler outer winds. It's a fragile balance, one that only persists because the star is hemorrhaging material fast enough to shield these molecules from further destruction. Yet for all its fury, NML Cygni's fate is sealed. Its erratic pulsations suggest a core running low on nuclear fuel, teetering toward collapse. When the end comes, it won't be quiet. This star's death throes will likely birth a Wolf-Rayet phase, stripping its outer layers to expose a searing helium core before the final supernova. Until then, it serves as a cosmic Rosetta Stone, teaching us how the universe's most massive stars recycle themselves. Every atom cast off today might one day form new worlds, carrying whispers of this shrouded giant's final acts across the galaxy. VY Canis doesn't dance alone, it drags a partner across the cosmos in a gravitational tango so vast, a single orbit takes 20 Earth years to complete. This isn't just any binary system, it's a celestial David and Goliath, where a red supergiant so large it could swallow our sun 1,000 times over looms beside a hot, compact blue companion barely a tenth its size. Their contrast isn't just visual, it's a study in extremes, with the red supergiant's cool, tenuous outer layers brushing against the blue star's searing radiation, creating a cosmic pressure cooker visible across 3,000 light-years. What makes this pair extraordinary isn't just their size difference, it's how they eclipse each other. Every 2 decades, the blue star vanishes behind its crimson counterpart for 18 grueling months, plunging the system into an eerie dimness detectable even with backyard telescopes. But the real spectacle happens when roles reverse. As the smaller star skims behind the supergiant, its intense ultraviolet light pierces the red giant's atmosphere like a spotlight through fog, ionizing gases and revealing structures typically hidden from view. Astronomers call this a natural coronagraph, a rare opportunity to map a supergiant's outer reaches without the glare of its core blinding our instruments. The precision of these eclipses transforms VY Canis into a cosmic measuring tape. By timing how long each star disappears and analyzing the dip in brightness, scientists calculate their sizes with jaw-dropping accuracy. We know the red supergiant's radius stretches 1,600 times wider than the Sun, so vast that light takes 6 hours to travel from its core to its outermost vaporous layers. The blue companion, though petite by comparison, punches above its weight with surface temperatures hitting 30,000 Kelvin, bathing its sluggish neighbor in enough X-rays to strip atoms bare. Animations of their orbit reveal a mesmerizing interplay of forces. The red supergiant's gravity tugs streams of gas from its own bloated atmosphere, funneling them toward the blue star in a shimmering accretion bridge. Meanwhile, the smaller star's fierce winds carve a cavity in the supergiant's outer haze, like a speedboat churning through mist. These interactions aren't just beautiful, they're teaching us how massive stars exchange material, a process that might explain bizarre hybrid stars found elsewhere in the galaxy. The most startling discovery, the red supergiant isn't as round as we thought. As it spins, centrifugal forces flatten it into a squashed sphere, while gravitational tides from its companions stretch it further into a teardrop shape. This distortion affects how light escapes during eclipses, creating subtle brightness quirks that, when decoded, reveal the star's internal structure down to the convection patterns in its outer layers. VY Canis 20-year waltz is more than a spectacle, it's a masterclass in stellar physics. With each eclipse, we refine our models of how stars live, interact, and ultimately die. And as the next eclipse approaches in the 2030s, new telescopes stand ready to uncover even deeper secrets, turning this cosmic duo into a beacon for understanding the universe's most colossal relationships. Mu Cephei isn't just a star, it's a cosmic jewel. William Herschel, the famed 18th century astronomer, didn't call it the Garnet Star for nothing. Even through modest telescopes, this red supergiant blazes with a deep, ruby glow so vivid it feels like the universe dipped it in wine. Located in the constellation Cepheus, 3,000 light-years away, Mu Cephei's color isn't just aesthetic, it's a thermometer. That rich crimson hue whispers secrets about its surface temperature, a relatively cool 3,600 Kelvin, making it one of the most visually distinct stars in the northern sky. But Mu Cephei's true legacy isn't just its beauty, it's its role as a cosmic benchmark. Astronomers use it as a standard for classifying other red supergiants, a celestial yardstick against which they measure stellar properties. Its spectral signature, the unique fingerprint of light it emits, has become a reference point, helping scientists calibrate telescopes and interpret data from distant stars. When you see Mu Cephei's distinct absorption lines in a spectrograph, you're looking at the template for how massive, aging stars behave. Point a telescope toward it, and the contrast is breathtaking. Against the pale splash of the Milky Way's backdrop, Mu Cephei pulses like a drop of blood on snow. Its light isn't steady, it flickers unpredictably, varying by nearly a full magnitude over years-long cycles. This isn't just random twinkling, it's the star's outer layers convulsing as it burns through the last of its nuclear fuel. Imagine a campfire where the logs shift and settle, sending up sudden flares. Only here, the logs are chunks of plasma larger than our solar system. Modern observations reveal even more drama. Mu Cephei is shedding mass at a staggering rate, its outer atmosphere streaming away in a stellar wind powerful enough to strip planets bare. Infrared images capture vast plumes of dust swirling around it, material that will one day seed new stars. And here's the twist: though it looks serene to our eyes, this star is a ticking time bomb. Within the next few million years, a blink in cosmic terms, it will detonate as a supernova, briefly outshining every other star in its galaxy. Yet for now, Mu Cephei remains a guidepost both for astronomers and stargazers. Its color, so intense it's visible even in light-polluted skies, makes it a favorite among amateur observers. Photographers chase it, stacking images to capture its garnet glow against the blue-white stars surrounding it. And every time a scientist classifies a new red supergiant, they're standing on Herschel's shoulders, using the Garnet Star as their Rosetta Stone. Mu Cephei isn't just a dying giant, it's a teacher, painting the universe's lessons in the boldest shade of red. V354 Cephei hides in plain sight, a cosmic chameleon masquerading as just another faint red dot in the Cepheus constellation. But zoom in, and this unassuming star reveals itself as one of the most unpredictable hypergiants ever discovered. Unlike the steady pulse of a lighthouse beacon, V354 Cephei flickers like a guttering candle, its brightness yo-yoing erratically between magnitudes over months or even years. Plot its light curve, and the graph looks less like a rhythmic wave and more like a seismometer during an earthquake. Spikes and troughs scattered chaotically, defying the orderly patterns most variable stars follow. This volatility isn't random noise, it's a cry for help from a star teetering on the edge of collapse. Stretching 1,500 times wider than our Sun, V354 Cephei's outer layers are so loosely bound that they slosh like water in a tilted bucket. Convection currents the size of solar systems churn beneath its surface, dragging pockets of hotter material upward in explosive surges that temporarily boost its luminosity. Then, as those bubbles cool and sink, the star dims again, creating the erratic light patterns that perplex astronomers. Infrared observations reveal even stranger behavior, vast plumes of titanium oxide and carbon monoxide swirling in its atmosphere, acting like celestial Venetian blinds that periodically shroud the star's glow. What makes V354 Cephei especially valuable to science is its rarity. While most pulsating hypergiants like Betelgeuse throb with predictable rhythms, this star's fits and starts offer a glimpse into a brief, turbulent phase of stellar evolution. Its instability suggests it's transitioning between nuclear fuel sources, a cosmic midlife crisis where it can't decide whether to contract or expand. Spectroscopic studies detect telltale signatures of helium and carbon burning in its core, evidence that it's exhausted its hydrogen and is now fusing heavier elements in a last-ditch effort to resist gravity's pull. The most compelling clue to V354 Cephei's future lies in its violent ejections. Every few decades, it coughs out a shell of gas equivalent to Jupiter's mass, visible as concentric rings in radio telescope images. These aren't gentle stellar winds, they're seismic belches, likely triggered by deep shocks rippling through the star's interior. Some theorists believe this could preface a future supernova, while others argue it might collapse directly into a black hole without the traditional fireworks. Either way, its death will rewrite the surrounding nebula, where new stars are already forming from its cast-off material. For now, V354 Cephei remains a puzzle, a reminder that even in the vast catalogue of the cosmos, some stars refuse to follow the rules. Every flicker, every dimming event is a breadcrumb trail leading us closer to understanding how the universe's mightiest stars dance on the edge of chaos. KY Cygni is the universe's quiet powerhouse, a star so colossal it defies expectations, yet so overlooked that even seasoned stargazers might miss its significance. Tucked away in the constellation Cygnus, this red supergiant is anything but average. Current estimates place its radius somewhere between 1,420 and 2,850 times wider than our Sun, a staggering range that reflects the challenges of pinning down a star that refuses to be neatly categorized. If placed at the center of our solar system, KY Cygni's tenuous outer layers would extend anywhere from just beyond Jupiter's orbit to nearly brushing against Saturn, depending on which measurements you trust. The confusion surrounding KY Cygni's true size stems from its distance roughly 5,000 light-years away, and its position deep within a dusty spiral arm of the Milky Way. Unlike nearby stars where parallax measurements give precise distances, KY Cygni's location forces astronomers to rely on indirect methods. By analyzing how interstellar dust dims and reddens its light, scientists must reverse engineer its properties, a process akin to guessing the wattage of a light bulb seen through heavy fog. Compounding the mystery, KY Cygni's luminosity might exceed 300,000 times that of the Sun, yet its cool surface temperature, around 3,500 Kelvin, masks its true power behind a deceptive crimson glow. Comparative diagrams reveal just how remarkable this star is. Stacked against better-known giants like Betelgeuse or Antares, KY Cygni dwarfs them in sheer volume, its hypothetical surface area large enough to engulf billions of Earths. Yet unlike those famous stars, KY Cygni lacks the name recognition, perhaps because its light takes millennia to reach us, or because its subtle variability doesn't grab headlines like Betelgeuse's dramatic dimming events. Infrared observations cut through the obscuring dust to reveal a star in turmoil, its outer layers billowing outward in great convective cells that channel heat like a slow-motion lava lamp. What truly sets KY Cygni apart is the delicate balance of forces within it. At this stage in its life, the star is caught between gravity's relentless pull and the explosive pressure of nuclear fusion, a battle that causes its size to fluctuate unpredictably. Spectroscopic studies detect titanium oxide in its atmosphere, a molecule that forms only in relatively cool stars and acts like a natural thermostat, absorbing specific wavelengths of light and complicating brightness measurements. This isn't just academic curiosity. Understanding KY Cygni's true nature helps calibrate our models for how the most massive stars evolve, the most humbling realization. KY Cygni's light-reaching telescopes today began its journey around the time humans were inventing written language. By now, this titan may have already met its fate, collapsing into a neutron star or erupting as a supernova, an event we won't witness for thousands of years. Until then, it stands as a testament to the universe's hidden giants, those unassuming behemoths that reshape galaxies without fanfare, reminding us that sometimes the most powerful forces are the ones we least expect. Scorpii isn't just a star, it's a beacon of the southern skies, a ruby jewel embedded in the constellation Scorpius that outshines nearly every other red supergiant in its celestial neighborhood. For observers below the equator, this stellar titan offers a rare spectacle, a deep crimson point of light flickering against the dense star fields of the Milky Way, its glow so saturated it seems to pulse with latent energy. At 9,000 light-years away, Scorpii's light takes millennia to reach us, but when it does, it tells a story of grandeur and instability written in slow, luminous waves. What sets this star apart isn't just its size, estimated at 1,400 times wider than the Sun, but its mesmerizing variability. Unlike the predictable rhythms of common variable stars, Scorpii's brightness shifts over years-long cycles, dimming and flaring with the erratic cadence of a dying ember. These changes aren't just superficial, they're symptoms of a star in existential turmoil. Convection currents larger than solar systems churn beneath its surface, dragging pockets of superheated plasma upward until they burst through the tenuous outer layers, temporarily boosting its radiance before fading back into obscurity. Astrophotographers treasure Scorpii for its visual drama. In wide-field images of the Scorpius-Centaurus region, the star stands out like a drop of blood spilled on black velvet, its hue intensified by interstellar dust that scatters blue light and lets only the deepest reds pass through. Long exposure shots reveal its neighborhood in breathtaking detail, nebulous tendrils and star clusters framing the supergiant in a cosmic diorama. But the real magic happens when professional telescopes zoom in. Infrared observations pierce the veil of dust surrounding Scorpii, exposing vast plumes of ejected materials swirling in intricate spirals, each one a testament to the star's violent shedding of its own atmosphere. The environment around Scorpii is just as fascinating as the star itself. Nestled within a dusty cocoon, it's clear this hypergiant isn't just fading quietly into the night. Spectroscopy uncovers molecules like titanium oxide and silicon monoxide in its vicinity, compounds typically found in the debris of stars tearing themselves apart. These dusty shrouds act like cosmic insulation, trapping heat and glowing faintly in the infrared, a reminder that even in death, Scorpii is sculpting its own memorial. And then there's the question of time. By the standards of stars, Scorpii is already on borrowed time. Burning through its nuclear fuel at a prodigious rate, its core is likely fusing heavier elements like carbon and oxygen in a desperate bid to stave off collapse. The clock is ticking. Within the next 100,000 years. This jewel of the southern sky could erupt in a supernova so brilliant it would outshine the full moon. Until then, Scorpii remains a celestial lighthouse, guiding astronomers to a deeper understanding of how the universe's most massive stars flirt with destruction before meeting their spectacular end. Persei isn't just a star, it's a time capsule suspended between two glittering cities of suns. Nestled within the Perseus double cluster, this crimson supergiant serves as both a landmark and a mystery, its glow flickering against one of the most densely packed stellar neighborhoods visible from Earth. What makes this star extraordinary isn't just its size, roughly 1,300 times wider than our Sun, but the sheer longevity of its recorded tantrums. Astronomers have tracked its luminosity swings since the late 19th century, creating a light curve that spans 3 generations of telescopic technology and captures the star's slow-motion struggle against collapse. The double cluster backdrop transforms S Persei into a cosmic showpiece. Through binoculars or telescopes, the view is staggering, 2 sparkling collections of young, hot stars framing the supergiant's deep red glow like diamonds encircling a burning ember. This setting isn't just scenic, it's scientifically revealing. The cluster's known distance, about 7,500 light-years, allows precise calculations of S Persei's true luminosity, which fluctuates between 90,000 and 200,000 times brighter than the Sun. Time-lapse sequences compiled from decades of observations show the star's mood swings in vivid detail, its brightness pulsing erratically as convective currents dredge up hotter material from its unstable interior. Historical records unveil patterns invisible to any single generation of observers. Glass photographic plates from the 1890s show S Persei in one of its dimmest phases, while mid-20th century observations capture sudden surges that temporarily made it the cluster's brightest resident. Modern digital sensors reveal subtler variations, micro-deminings that hint at vast dust clouds forming in its atmosphere, similar to Betelgeuse's infamous Great Dimming, but on an even grander scale. This century-spanning dataset makes S Persei a Rosetta Stone for understanding how evolved massive stars behave before their final explosions. Infrared imaging peels back another layer of intrigue. While visible light shows the star's turbulent surface, longer wavelengths expose its extravagant waste, great loops and arcs of ejected material stretching light years into space. These aren't smooth, symmetrical shells but twisted, knotted structures, sculpted by magnetic fields and the gravitational tug of neighboring stars. Some filaments glow particularly bright at certain infrared frequencies, betraying the presence of aluminum oxide dust, the same compound that gives rubies their color, making S Persei literally wrapped in its own cosmic jewelry. The most compelling revelation comes from spectroscopy. S Persei's light, when split into a rainbow, shows absorption lines that shift dramatically over time, evidence of supersonic shockwaves rippling through its extended atmosphere. These aren't gentle pulsations but seismic upheavals, with whole layers of the star sloshing like water in a shaken bowl. At times, the spectral lines split into multiple components, revealing that we're seeing not one coherent surface but overlapping regions moving at different velocities, a hallmark of a star losing cohesion. For all its instability, S Persei offers a rare constant: its celestial address. Unlike many hypergiants that drift alone through space, this star's membership in the double cluster provides an anchor point for researchers. By comparing its properties to the cluster's other stars, all born from the same gas cloud around 12 million years ago, astronomers can reconstruct how stellar mass and composition dictate a star's fate. S Persei's siblings, though younger, are destined to follow similar paths, allowing us to witness different chapters of a massive star's life story within a single, glittering frame. What comes next for this aging giant? Current models suggest it's entering the final 1% of its lifespan, perhaps just millennia away from detonating as a supernova. When that happens, the explosion will momentarily outshine its entire host cluster, casting new light literally on the surrounding stellar nurseries. Until then, S Persei keeps performing its slow, luminous dance, a beacon to patient observers across centuries and civilizations, reminding us that some of the universe's greatest dramas unfold not in seconds but in lifetimes. WHG 64 doesn't just break the mold, it reshapes it entirely. Floating alone in the Large Magellanic Cloud, 163,000 light-years from home, this crimson behemoth is the ultimate cosmic exile. At 1,540 times wider than our Sun, it dwarfs nearly every other star in its dwarf galaxy neighborhood, an isolated titan wrapped in a spectacle unlike anything in the Milky Way. James Webb's infrared gaze has peeled back the layers of its mystery, revealing not a typical spherical hypergiant, but a star cocooned within a colossal dust torus, a glowing donut of stellar debris 3 light-years across that spins like a cosmic carousel around its dying heart. The numbers alone make WOHG 64 extraordinary. Its surface simmers at just 3,200 Kelvin, cool enough for complex molecules to form in its atmosphere, something nearly impossible for most stars this massive. That relative chill allows dust grains to condense in its outer layers, creating the thick shroud that gives this star its bizarre silhouette. Unlike the chaotic plumes surrounding other hypergiants, WOHG 64's dust forms an eerily symmetrical ring, shaped by magnetic fields and rotation into a near-perfect disk when viewed pole-on. The effect is celestial sleight of hand. What appears at first glance to be a dying star is actually a brilliant core peeking through a keyhole of its own making. Zoom in with Webb's mid-infrared instrument and the details become breathtaking. The dust torus isn't smooth, it's fractured into concentric bands like tree rings recording violent outbursts from the star. Spectral analysis reveals these ripples contain aluminum oxide and silicates, materials typically found in rocky planets rather than stellar atmospheres. Somehow, WOHG 64 is forging the building blocks of worlds even as it disintegrates. The most surprising discovery: a vast gap separates the star from its inner dust rim, a cleared zone likely swept clean by intense radiation pressure, creating a stellar version of the snow line in protoplanetary disks. What makes this star truly unique is its evolutionary dead-end status. While most hypergiants eventually explode as supernova, WOHG 64's extreme mass loss ejecting Earth's weight in material every second might leave too little behind for a traditional explosion. Instead, it could collapse directly into a black hole with little fanfare, its outer layers having already bled away into the surrounding nebula. The dust torus isn't just a curiosity, it's a funeral shroud being woven in real time. Yet within this melancholy lies cosmic poetry. The same dust that obscures WOHG 64's light also enhances its infrared glow, making it one of the most luminous objects in the local group at those wavelengths. Every atom fleecing its surface will one day seed new stars in the Large Magellanic Cloud, a phoenix ensuring its rebirth even as it fades. For now, this solitary giant stands as a bridge between galaxies, challenging what we thought possible for stellar structure and reminding us that the universe always keeps a few secrets in its farthest corners. RSGC 1F01 lurks in the shadows of our galaxy's bustling core, a titan hiding in plain sight. Nestled within the RSGC-1 star cluster, a glittering metropolis of young, massive stars just 19,000 light-years from Earth, this hypergiant would remain invisible without the piercing gaze of infrared telescopes. Unlike the vibrant blues and whites of its cluster siblings, RSGC 1F01 cloaks itself in dust, its crimson glow smothered by the thick interstellar debris near the Milky Way center. But when viewed in infrared, the illusion shatters. A star so luminous it outshines the Sun by nearly 500,000 times, its heat signatures burning through the cosmic smog like a lighthouse through storm clouds. False color images from observatories like Spitzer and James Webb reveal RSGC 1F01's true nature. Where optical telescopes see only darkness, infrared unveils a searing orb swaddled in swirling dust, its surface temperature soaring to 3,600 Kelvin. The star's radiation carves cavities in the surrounding nebula, sculpting towering pillars of gas that glow eerily in the processed images, vivid reds and oranges representing heat rather than visible light. These aren't just pretty pictures, they're cosmic roadmaps showing astronomers how energy escapes from stars buried in the galaxy's dustiest neighborhoods. The discovery of RSGC-1 F01 rewrote expectations for stellar clusters. Before infrared astronomy, scientists assumed the RSGC-1 region was dominated by Wolf-Rayet stars, hot, compact objects burning their final fuel. But RSGC-1 F01 proved something far rarer existed in the mix, a red supergiant nearing the end of its life, already shedding its outer layers in preparation for a supernova. Its spectral lines tell a story of turmoil, with titanium oxide and carbon monoxide molecules swirling in its extended atmosphere, betraying the star's instability. Radio observations add another layer, capturing maser emissions, natural lasers created when its intense radiation excites water molecules in the surrounding dust. What makes this star particularly fascinating is its environment. The RSGC-1 cluster is a stellar nursery on steroids, packed with dozens of massive stars crammed into a space smaller than the distance between the Sun and Alpha Centauri. In this chaotic dance, RSGC-1 F01 stands out not just for its size, but for its resilience. While smaller stars in dense clusters often get ejected by gravitational interactions, this hypergiant holds its ground, its sheer mass anchoring it like a boulder in a raging river. The implications stretch beyond a single star. RSGC-1 F01's existence suggests that many more hidden giants could be lurking near the galactic center, obscured by dust but radiating fiercely in infrared. Future telescopes equipped with even more sensitive infrared detectors might reveal a population of these enigmatic objects, rewriting our understanding of how stars form and evolve in the universe's most crowded environments. For now, RSGC-1 F01 remains a beacon, not of light but of heat, a reminder that sometimes the cosmos hides its most spectacular wonders just out of sight. HD 269,551 doesn't play by the rules. While most stars on this list earn their place through sheer size, this blue supergiant from the Large Magellanic Cloud dominates through pure, unfiltered intensity. Imagine taking our Sun's entire energy output and multiplying it by 2 million. That's the staggering luminosity packed into a sphere just 30 times wider than our home star. If placed at the center of our solar system, HD 269,551 wouldn't even reach Mercury's orbit, yet its blistering 45,000 Kelvin surface would vaporize every planet instantly, boiling away atmospheres like morning fog under a blowtorch. The secret lies in its color. That piercing azure glow isn't just for show. Unlike the cool, bloated red supergiants we've explored, HD 269,551 burns hot and fast, fusing hydrogen at a pace that would make lesser stars shudder. Its spectral lines reveal a composition laced with ionized helium and nitrogen, telltale signs of material processed through the Carnot cycle, a high-temperature nuclear reaction chain that operates like a cosmic turbocharger. This isn't gentle starlight, it's a continuous thermonuclear explosion contained by gravity's grip, pumping out enough ultraviolet radiation in 1 second to power human civilization for centuries. Hubble's portraits capture the star's transformative power. Surrounding HD 269,551 stretches a vast emission nebula, its delicate filaments glowing electric blue under the star's unforgiving glare. These aren't static clouds, they're battlefields where the star's supersonic winds, racing outward at over 2,000 miles per second, collide with interstellar gas. The shock fronts ripple through space like cosmic sound waves, compressing hydrogen into glowing knots that eventually collapse into new stars. In HD 269,551 case, the stellar wind carries enough punch to strip away an entire solar system's worth of material every few thousand years. What makes this blue giant truly remarkable is its influence on galactic chemistry. Spectroscopy shows its surroundings enriched with oxygen, neon, and magnesium elements cooked in its core and blasted into space by the relentless winds. These heavy atoms will eventually seed future generations of stars and planets, meaning HD 269,551 isn't just a celestial spotlight, it's a chemical factory reshaping its corner of the universe. The nebula's intricate structures, captured in long-exposure images, show bubbles within bubbles, evidence of periodic outbursts where the star temporarily doubled its wind speed, carving intricate caverns in the interstellar medium. Yet for all its ferocity, HD 269,551 lives on borrowed time. Blue supergiants are stellar mayflies. Its current phase might last just a few million years before it either collapses directly into a black hole or detonates as a type Roman II supernova. When that day comes, the shockwave will trigger new star formation across the nebula, while the explosion's light will briefly outshine the entire Large Magellanic Cloud. Until then, this blue powerhouse continues its double role, both destroyer and creator, its light a beacon illuminating one of the universe's most extreme balancing acts. R136A1 doesn't just push the limits of stellar physics, it obliterates them. Lurking in the heart of the Tarantula Nebula, 163,000 light-years away, this behemoth tips the cosmic scales at 215 times the mass of our Sun, burning with the fury of nearly 8 million suns combined. Hubble's ultraviolet images reveal it as the crown jewel of a glittering star cluster, its searing light carving cavities in the surrounding gas like a blowtorch through cotton candy. If placed in our solar system, even at the distance of Pluto, R136A1's radiation would sterilize Earth's surface in seconds, a reminder that some stars aren't just luminous, they're apocalyptic. Theories about how such a monstrosity formed read like cosmic fan fiction. One camp suggests it's the product of stellar cannibalism, smaller stars in the dense cluster colliding and merging like celestial Frankenstein monsters. Others argue it grew from a nebula so packed with gas that gravity couldn't resist forming a single gargantuan object. The most tantalizing idea, R136A1 might be a failed multiple system, where 3 or 4 massive stars attempted to form separately but got so tangled in each other's gravity that they fused into one ultimate powerhouse. Simulations show these scenarios aren't mutually exclusive. In the Tarantula Nebula's violent nursery, all 3 processes could have conspired to birth this record-shattering titan. Hubble's close-ups expose the star's ruthless impact on its environment. The nebula around R136A1 glows electric blue in false color images, ionized by ultraviolet photons so energetic they strip electrons from atoms light-years away. Shadowy pillars of denser gas resist the onslaught, their silhouettes evoking the famous Pillars of Creation. But here, the sculpting force isn't just starlight, it's a hurricane of radiation and particle winds moving at 3,000 miles per second. Spectroscopy reveals these winds carry enough metal-rich material each year to build 30 Earths, a testament to the star's desperate struggle against its own gravity. Yet R136A1's reign will be tragically brief. Stars this massive burn through their nuclear fuel like billionaires squandering fortunes. Its expected lifespan barely cracks 2 million years, a cosmic blink compared to our Sun's 10 billion-year retirement. Already, its core likely fuses silicon into iron at temperatures exceeding 1 billion Kelvin, inching toward the fusion dead end that spells supernova. When collapse comes, it won't just explode. Current models suggest it might trigger a pair instability supernova, a runaway thermonuclear detonation so violent it leaves no remnant behind, annihilating itself completely in a flash brighter than some galaxies. The star's greatest legacy, though, lies in the heavy elements it's forging. Every atom of gold, platinum, or uranium in the universe was born in such cataclysms. R136A1's eventual death will seed future generations of stars and planets, its ashes literally becoming the building blocks of alien worlds. For now, it stands as a cosmic rebel, proof that nature, when given the right conditions, doesn't just break rules, it rewrites them. Eta Carinae isn't just a star, it's a cosmic powder keg with a lit fuse. Nestled 7,500 light-years away in the Carinae constellation, this binary system consists of two stellar monsters locked in a lethal embrace. The primary star alone weighs 90 times more than our Sun and burns 5 million times brighter, while its smaller but equally ferocious companion whips around it every 5.5 years in an orbit so tight their stellar winds collide with the force of galaxy-scale hurricanes. But what makes Eta Carinae legendary isn't just its present violence, it's the apocalyptic tantrum it threw in the 1840s. An outburst so colossal it briefly became the second brightest star in Earth's night sky, visible even in broad daylight. That event, dubbed the Great Eruption, wasn't a typical stellar flare. Over 2 decades, Eta Carinae ejected at least 20 solar masses of material at breakneck speeds, forming the bizarre homunculus nebula we see today. Historical drawings from the era capture the astonishment of astronomers watching a dim star suddenly outshine Sirius. Modern telescopes reveal the aftermath in breathtaking detail. Twin lobes of glowing gas expanding outward like a cosmic hourglass, each tipped with ragged filaments where shockwaves rip through interstellar space. Hubble's ultraviolet vision exposes the nebula's hidden structure, great ripples and knots in the gas, frozen echoes of the explosion's chaotic energy. Theories about what triggered the eruption read like astrophysical detective stories. Some suggest the primary star's radiation pressure nearly overcame gravity, causing its outer layers to balloon until they were violently shed. Others posit that the companion star's periodic close approaches stir up titanic instabilities, like a spoon swirling cream into coffee, only here the cream is superheated plasma. The most compelling clue comes from light echoes, delayed reflections of the 1840s event bouncing off distant dust clouds. By analyzing these cosmic replays, astronomers found the eruption spectrum matches no known stellar outburst, suggesting Eta Carinae invented its own brand of catastrophic behavior. Today, the system remains wildly unpredictable. X-ray observatories catch violent flares when the star's colliding winds create temperatures exceeding 60 million Kelvin, hotter than the Sun's core. Infrared images reveal vast dust lanes spiraling through the homunculus, while radio telescopes detect maser emissions from water molecules caught in the turmoil. Even the nebula's shape defies expectations. Its bipolar lobes aren't perfectly symmetrical but warped and dimpled, as if sculpted by unseen forces. The real question isn't if Eta Carinae will explode again, but when and how catastrophically. Current models suggest the primary star has burned through its nuclear fuel so recklessly that it could collapse into a black hole within the next few millennia. When that happens, the resulting hypernova might unleash a gamma ray burst powerful enough to strip ozone layers from planets thousands of light-years away. For now, Eta Carinae keeps astronomers on edge, its every flicker scrutinized for signs of the next great eruption. A reminder that the universe's most spectacular fireworks often come from stars dancing on the edge of self-destruction. WR102K isn't just another Wolf-Rayet star. It's a cosmic blowtorch carving its name into the heart of the Milky Way. Nestled just 26,000 light-years from Earth, deep in the galaxy's chaotic central region, this star is a rare gem even among its exotic kind. Unlike the bloated red supergiants we've explored, WR102K is a stripped-down, scorching core, a stellar heavyweight that shed its outer layers to reveal a blistering engine of pure nuclear fury. With surface temperatures soaring past 200,000 Kelvin, it doesn't just shine. It screams its existence into the void with enough ultraviolet radiation to ionize atoms light-years away. What truly sets WR-102K apart is the hurricane raging from its surface. Its stellar wind howls at 3,200 kilometers per second, fast enough to cross the continental United States in less than a second. That's not a gentle breeze, it's a supersonic freight train of charged particles, tearing away the star's remaining atmosphere at a rate that would vaporize our sun in mere millennia. Spectroscopy reveals why this wind is so peculiar, rich in carbon and oxygen, but nearly devoid of hydrogen, the telltale signature of a star that's burned through its primary fuel and is now fusing heavier elements in a last-ditch effort to delay collapse. But the real showstopper is the Peony Nebula, the glowing shroud that gives this star its nickname. Infrared telescopes like Spitzer and James Webb reveal a spectacle unlike anything else in our galaxy. Vast filamentary clouds of dust and gas, twisted into intricate shapes by WR-102K's relentless winds. The nebula glows in false color images like a cosmic rose, its petals stretching 15 light-years across and shimmering with the heat of newly forged heavy elements. Unlike the symmetrical shells around other Wolf-Rayet stars, the Peony's structure is chaotic, its spirals and knots suggesting violent eruptions where the star has coughed up massive chunks of its own interior. Zoom in closer and the details become even more fascinating. The nebula isn't just passively reflecting light, it's fluorescing, its molecules excited by WR-102 cause intense radiation into emitting specific wavelengths. Sulfur glows red, hydrogen burns green, and oxygen radiates blue in processed images, creating a celestial stained glass window. Radio observations add another layer, capturing maser emissions natural lasers, where water molecules in the nebula amplify specific frequencies, turning parts of the cloud into interstellar radio transmitters. The most startling revelation, WR-102K might be one of the most luminous stars in the Milky Way, potentially shining with the light of 3 million suns. That's a controversial claim. Some astronomers argue dust between us and the star dims its true brilliance, while others believe we're still underestimating its power. Either way, this star's fate is sealed. Wolf-Rayet stars live fast and die young, and WR-102K is likely within a few 100,000 years of its grand finale, a supernova or even a gamma-ray burst that could light up the galactic center like a second sunrise. Until then, it stands as a monument to stellar extremity, a reminder that even in the crowded core of our galaxy, nature finds ways to surprise us with celestial violence beyond imagination. The pistol star doesn't just shine, it detonates light. Hidden within the quintuplet cluster near the Milky Way's core, 25,000 light-years from Earth, this blue hypergiant is nature's equivalent of a cosmic flashbulb, erupting with enough violence to permanently alter its own destiny. Its name comes not from its shape, but its impact. The Pistol Nebula surrounding it resembles a ghostly smoke ring, the aftermath of apocalyptic outbursts that ejected 10 times the sun's mass in mere millennia. If placed where our sun sits, the Pistol star's ultraviolet radiation would dismantle Earth's atmosphere in hours, yet from our vantage point, it's completely invisible without infrared telescopes. This invisibility is a cosmic irony. The Pistol star radiates with the luminosity of 10 million suns, but its light battles an interstellar obstacle course. Thick dust clouds between us and the galactic center absorb nearly all its visible light, transforming what should be one of the brightest stars in the sky into a faint infrared whisper. Multi-wavelength composites reveal the truth. Hubble's optical images show only darkness, while Spitzer's infrared eyes unveil a searing blue heart wrapped in the Pistol Nebula's glowing tendrils. These contrasting views stitch together a story of catastrophic loss. The nebula's complex filaments are the star's own flesh, hurled outward during violent eruptions 6,000 years ago when human civilizations were first recording history. The Pistol star's tantrums defy ordinary stellar behavior. Typical supergiants shed mass slowly like steady ocean breezes. This hyper-luminous variable expels material in tsunamis, gigantic eruptions where chunks of its atmosphere accelerate to escape velocity in sudden, convulsive bursts. Spectroscopy uncovers the aftermath. Helium and nitrogen dominate its exposed layers, proof that fusion byproducts normally buried deep in the core have been scraped bare by these self-inflicted wounds. The Pistol Nebula's intricate knots and braids, captured in radio telescope data, map the trajectory of these eruptions like forensic evidence at a cosmic crime scene. But the real mystery is timing. Most stars this massive live fast and die young, yet the Pistol star seems to be cheating death. Its current mass, likely still 100 times the Sun's, suggests it should have collapsed into a black hole by now. Some theories propose its eruptions act like pressure valves, ejecting enough material to temporarily stabilize its core. Others speculate it might be a stellar merger, its extra mass buying it more time through gravitational subterfuge. Either way, its fate is sealed when collapse finally comes. It won't just go supernova. It might trigger a pair instability explosion, vanishing entirely in a fireball visible across the universe. For now, the Pistol star remains a paradox, a beacon of destruction hidden in plain sight, its brilliance smothered by the very dust it helped create. Every atom it blasts into space carries a message about how the universe's most volatile stars sculpt their own endings, rewriting the rules even as they burn toward oblivion. LBV 18620 doesn't just burn, it crackles with invisible force. Tucked away 30,000 light-years from Earth, this luminous blue variable hides a secret beneath its searing exterior, a magnetic field so intense it could rearrange atoms like iron filings near a magnet. Clocking in at a staggering 30,000 Gauss, 3,000 times stronger than our Sun's, this star's magnetic grip shapes its every eruption, twisting stellar winds into spirals and funneling radiation into cosmic searchlight beams. Radio telescopes capture the chaos in vivid detail, loops of plasma trapped along magnetic field lines, their synchrotron emissions painting the surrounding nebula with eerie, polarized light. The mystery deepens when we ask why. Most LBVs are temperamental divas, prone to violent outbursts without magnetic meddling. Yet LBV 18620 field is so powerful it suggests something extraordinary beneath the surface. One camp of astronomers argues we're seeing the ghost of a neutron star, a dense remnant left behind when this star's hypothetical twin exploded long ago. Their smoking gun, peculiar X-ray flares that flicker with clockwork precision, hinting at a hidden companion dragging its magnetic footprint through the hypergiant's winds. Others counter that the star might be a freak of nature, its core generating magnetism through dynamo effects usually reserved for smaller, faster-spinning stars. False color radio images reveal the drama playing out across light years. The star's magnetosphere carves a cavity in the interstellar medium, its shockwaves glowing gold in processed data, while magnetic filaments streak outward like cosmic spider silk. These filaments aren't static, they writhe as the star's rotation twists them into helical coils, a phenomenon normally seen around pulsars, not unstable supergiants. Spectroscopy adds another twist, emission lines split into multiple components by Zeeman splitting, a telltale sign of atoms straining against magnetic forces strong enough to warp quantum states. The most tantalizing clue comes from light echoes. When LBV 18620 erupted in the 1990s, briefly outshining every star in its galaxy, the flash illuminated nearby dust clouds. Analyzing these delayed reflections revealed something bizarre. The explosion spectrum contained features typical of magnetically confined plasma, as if the star's entire surface had become a temporary magnetic prison. Whether lone wolf or cosmic duo, LBV 18620 challenges every assumption about stellar magnetism. Its existence suggests that somewhere between the calm order of main sequence stars and the chaos of hypergiants, nature finds ways to impose its own strange rules, turning what should be a simple ball of plasma into a laboratory for physics we've barely begun to understand. HD 93129A doesn't just reside in the Carinae Nebula, it owns it. This O-type Leviathan, one of the most luminous stars in our galaxy, serves as the blazing heart of Trumpler 14, a star cluster so densely packed it feels like a celestial stadium under construction. With a surface temperature scorching at 50,000 Kelvin, 9 times hotter than our Sun, HD 93129A pumps out ultraviolet radiation so intense it strips electrons from atoms light years away, transforming vast swaths of surrounding gas into glowing plasma. Hubble's wide-field images capture the star's dominance, a searing blue-white beacon amid swirling nebula tendrils, its light sculpting colossal cavities in the cosmic dust like a blowtorch through fog. Zoom in on the cluster, and the sheer violence of this environment becomes breathtaking. Trumpler 14 isn't just a collection of stars, it's a demolition derby of stellar winds, where HD 93129A supersonic outflows collide with those of its neighbors at speeds exceeding 2,000 miles per second. These collisions generate shockwaves visible in X-ray and radio wavelengths, rippling through the nebula and triggering chain reactions of star formation. The star's photons are just as destructive, ionizing hydrogen atoms in the surrounding H-Roman 2 region and making the gas fluoresce in vivid pinks and reds, a process astronomers call photoionization. This isn't passive starlight, it's a continuous cosmic power wash scrubbing the interstellar medium raw. What makes HD 93129A particularly fascinating is its rarity. O-type stars like this account for less than 1 in a million of the Milky Way's stellar population, yet their impact is disproportionate. Each one pumps out enough energy in a single day to power human civilization for centuries. Spectroscopy reveals HD 93129A's composition, its atmosphere laced with ionized helium and nitrogen, the chemical fingerprints of nuclear reactions running at full throttle. Unlike cooler stars that convect heat like a simmering pot, this star's energy races straight to the surface, escaping as a hurricane of radiation that peels away its own outer layers at a rate of 1 Earth mass every few thousand years. The wider context of Trumpler 14 adds another layer to the drama. This cluster is a stellar nursery on overdrive, home to dozens of massive stars born from the same gas cloud just a few million years ago, a blink compared to our Sun's age. Infrared images reveal protostars still forming in the shadow of their giant siblings, their faint glow smothered by HD 93129A's brilliance. The interplay between creation and destruction here is relentless. The same radiation that erodes nearby gas clouds also compresses their edges, triggering gravitational collapses that birth new stars. It's a cosmic chicken and egg scenario unfolding in real time. For all its ferocity, HD 93129A's reign will be brief. Stars this massive burn through their fuel with reckless abandon, their lifespans measured in mere millions rather than billions of years. Already, its core likely fuses helium into heavier elements, inching toward the catastrophic chain reaction that will one day rip it apart in a supernova. When that happens, the shockwave will ripple through Trumpler 14, potentially triggering a new wave of star formation, a final act of destruction seeding future creation. Until then, HD 93129A remains a lighthouse of the Carinae Nebula, its ultraviolet beacon etching its legacy into the fabric of interstellar space. Cygnus OB212 doesn't just shine, it defies logic. Even from 5,000 light-years away, buried in the galactic plane's dust-choked depths, this star punches through the cosmic haze with the luminosity of nearly 6 million suns. Its light, traveling since the dawn of human civilization, arrives at Earth dimmed by interstellar smog, yet still bright enough to challenge astronomers' tools. If placed at the distance of Alpha Centauri, Cygnus OB212 would cast shadows on Earth brighter than a full moon, its ultraviolet radiation baking our atmosphere to a crisp in hours. Classifying this celestial powerhouse is like trying to box a hurricane. Its spectrum straddles the line between blue hypergiant and luminous blue variable, with emission lines so broad they suggest a star tearing itself apart atom by atom. Hydrogen is scarce in its atmosphere, replaced by helium and nitrogen fusion byproducts, evidence that stellar winds have peeled away its outer layers like an onion, exposing the nuclear forge beneath. The star's temperature fluctuates wildly too, swinging between 25,000 and 40,000 Kelvin over years-long cycles, as if it can't decide whether to be a searing blue beacon or a slightly cooler cosmic blowtorch. Infrared observations reveal the true scale of Cygnus OB212 violence. Nestled in the Cygnus OB2 association, a bustling stellar nursery packed with hundreds of massive stars, it dominates its peers like a grizzly among wolves. Shockwaves from its solar wind carve bubble like cavities in surrounding nebulas, visible in radio telescope data as ghostly spheres expanding at 2,000 miles per second. The star's photosphere isn't a calm surface but a maelstrom of plasma loops, their dynamics revealed by Doppler shifts that show some regions boiling upward while others plunge into the depths at terrifying speeds. The most tantalizing clue to its nature lies in peculiar spectral lines from ionized iron. These features, usually seen in the accretion disks of black holes, suggest Cygnus OB212 might be encircled by a torus of superheated debris, either remnants of past eruptions or material stolen from a hypothetical companion star. Some theorists even speculate it could be a failed supernova, a star so massive it should have exploded centuries ago but continues burning through exotic nuclear reactions. Every observation peels back another layer of mystery, proving that even in a universe full of giants, Cygnus OB212 stands as a law unto itself. Zeta Puppis isn't just racing through space, it's making a violent escape. Hurtling at 60 kilometers per second, this blue supergiant tears through the interstellar medium like a cosmic bullet, leaving a glowing bow shock in its wake that stretches over 4 light years. If stars could scream, Zeta Puppis would be the universe's primal roar. Its trajectory so reckless it's effectively fleeing the scene of a gravitational crime. The mystery of how it got this speed starts with a stellar breakup. Most massive stars like Zeta Puppis are born in dense clusters, surrounded by siblings that exert gravitational pulls in all directions. But here's the twist: when 2 or 3 of these stars get too close, their gravitational dance can turn chaotic. Picture a game of cosmic pinball. If one star gets slingshot too close to the cluster's core, the combined gravity of its neighbors can fling it outward at unimaginable speeds. That's likely what happened to Zeta Puppis. Simulations tracing its path backwards suggest it was violently ejected from the Trumpler 10 cluster over 2 million years ago, a celestial outcast banished by its own kind. What makes this runaway star truly mesmerizing is the destruction it leaves in its path. As it plows through space, its fierce stellar wind blasting outward at 2,000 kilometers per second collides with interstellar gas, compressing it into a glowing arc ahead of the star. Infrared images reveal this bow shock in stunning detail, a shimmering wall of heated particles resembling the wake of a speedboat on a cosmic scale. The force is so intense that it preheats the gas Zeta Puppis hasn't even reached yet, ionizing hydrogen atoms and leaving a breadcrumb trail of disturbed space. But Zeta Puppis isn't just a destroyer, it's also an unwitting architect. The turbulence it creates in its wake can trigger pockets of gas to collapse, seeding new star formation. It's a paradox. A star born from chaos now sows chaos itself, ensuring its legacy persists long after it vanishes into the galactic void. Motion simulations show its future isn't any less dramatic. Within the next million years, Zeta puppies will likely break free of the Milky Way's spiral arms entirely, becoming a hypervelocity star destined to roam intergalactic space alone. By then, the cluster that expelled it may have scattered, its sibling stars drifting apart, proof that in the universe, even the mightiest bonds can shatter in an instant. For now, Zeta puppies remains a blazing reminder that sometimes the most powerful stars aren't those that stay, they're the ones that refuse to be held back. Sigma Orionis isn't just a star, it's a celestial dynasty, a 5-member royal family bound by gravity in an intricate cosmic dance. At first glance, it blends into Orion's glittering belt as a single point of light. But peer closer, and this system reveals itself as a nested hierarchy of stellar power, where each member exerts its influence with gravitational precision. The primary star, Sigma Orionis AB, anchors the system, a searing binary pair so close they orbit each other in just 143 days, their combined light blazing 20,000 times brighter than our Sun. Around them whirl 3 lesser but equally fascinating siblings, a hot blue star 10 times the Sun's mass, a smaller but fiercely magnetic companion, and a distant outlier whose very existence challenges how we think massive star clusters form. Orbital animations of this quintuple system resemble a spinning top within a top, a mesmerizing choreography where each participant follows precise, predictable paths. Spectroscopy splits their combined light into individual fingerprints, revealing temperatures ranging from 30,000 Kelvin for the hottest members down to a cool 9,000 for the smallest. The real surprise lies in their ages. While most multiple star systems form together from the same gas cloud, Sigma Orionis's outliers show chemical compositions suggesting they were kidnapped, gravitationally captured from other parts of the Orion Nebula complex during its chaotic infancy. Their forced family portrait gives astronomers a rare chance to study how star clusters evolve through cosmic collisions. The system's fiercest drama unfolds at its heart, where the AB binary dominates. Ultraviolet telescopes catch their stellar winds colliding like dueling hurricanes, generating X-rays hot enough to melt asteroids into vapor. Meanwhile, the magnetic B component, just 6 times the Sun's mass, spits out flares so powerful they briefly outshine the entire system, twisting its magnetic field lines into knots visible through polarized light filters. Such violent contrasts make Sigma Orionis a natural laboratory for testing how stars influence each other's evolution. The primary duo's intense radiation strips material from their smaller siblings, creating swirling accretion streams captured in infrared by the James Webb Space Telescope. These feeding frenzies may explain why some stars in the system burn hotter and die younger than their mass alone would predict. Perhaps most intriguing is what Sigma Orionis teaches us about stellar nurseries. Typically, stars form at safe distances to avoid gravitational turmoil. Yet here, 5 massive stars coexist in a space smaller than Pluto's orbit, a density that should trigger catastrophic collisions. High-resolution radio maps solve part of the puzzle, showing the system is surrounded by a vast disk of debris, the shattered remains of a 6th member that strayed too close and was torn apart centuries ago. This cosmic buffer zone absorbs gravitational disturbances, acting like a stellar shock absorber that keeps the surviving members in stable orbits. Every observation peels back another layer of mystery. Doppler tracking reveals subtle tugs between the stars, hinting at unseen planets or brown dwarfs hiding in the shadows. Meanwhile, the outlier star, separated by over 10,000 astronomical units, carries scars of its violent past in its unusual spin rate, as if still dizzy from the gravitational encounter that trapped it here. Sigma Orionis doesn't just defy expectations, it rewrites the rules, proving that even in a universe governed by physics, the birth of stars remains a beautifully chaotic affair. Theta 1 Orionis C isn't just another star in Orion's sword, it's the dazzling conductor of an interstellar light show, the cosmic engine that brings the Orion Nebula to life. Nestled at the heart of the trapezium cluster, this O-type giant pumps out ultraviolet radiation so fierce it ionizes an area of space 20 light-years across, transforming the surrounding gas into the glowing masterpiece we see through telescopes. Without Theta 1 Orionis C's relentless energy, the nebula would collapse into darkness, a cold cloud of hydrogen with none of the ethereal glow that makes it a favorite among stargazers. Hubble's razor-sharp images reveal the star's dominion in breathtaking detail. Theta 1 Orionis C blazes at the center of a celestial hurricane, its stellar winds screaming outward at 2,000 kilometers per second, fast enough to cross the United States in under 2 seconds. These winds don't just race through empty space, they collide with slower-moving gas, sculpting vast cavities and shockwaves that ripple through the nebula like cosmic sound waves. Close-ups of these collision zones show intricate structures, filaments twisted into knots, bubbles within bubbles, and delicate tendrils of gas heated to thousands of degrees. The effect resembles a flame frozen in mid-flicker, captured with such precision you can almost hear the roar of interstellar turbulence. But the star's true legacy lies in its ruthless influence on budding planetary systems. The trapezium cluster is packed with protoplanetary disks, flat, rotating rings of gas and dust where planets form. Without Theta 1 Orionis C, these disks might quietly evolve into solar systems like our own. Instead, they face an ultraviolet onslaught. Hubble's ultraviolet vision catches the carnage in real time, disks warping under the radiation, their outer layers boiling away into space like steam off a hot skillet. Some disks, positioned at just the right angle, cast long shadows across the nebula, their silhouettes stretching light years like cosmic sundials. Yet this destruction isn't senseless, it's transformative. The same radiation that strips away fragile atmospheres also triggers chemical reactions within the surviving disks, forging complex organic molecules that might one day seed life on more sheltered worlds. Theta 1 Orionis sees violent winds even compress nearby gas, triggering new waves of star formation. It's a paradox. The star that tears down also builds up, its energy both executioner and architect of cosmic evolution. The most haunting revelation comes from spectroscopy. Theta 1 Orionis sees light split into wavelengths, reveals it's not just massive, it's practically hemorrhaging material, shedding an Earth's worth of mass every few thousand years. Doppler shifts in its spectral lines betray supersonic turbulence in its atmosphere, as if the star's very surface is a storm-tossed ocean of plasma. And lurking in those spectra is a chilling clue. The star's composition suggests it's already burning helium in its core, a sign it's racing toward an early death. For now, Theta 1 Orionis C reigns supreme, its brilliance etching patterns into the nebula that will persist long after the star itself explodes. When that day comes, the shockwave will ripple through Orion's stellar nursery, compressing gas into new generations of stars, an echo of the very process that birthed this luminous titan. Until then, it stands as both destroyer and creator, proving that in the cosmos, the line between chaos and beauty is thinner than we ever imagined. Pisces 24-1 once wore the crown as the universe's mightiest star, until Hubble pulled back the curtain and revealed an even more fascinating truth. Initially celebrated for a staggering mass of 200 to 300 suns, this colossal beacon in the Scorpius constellation had astronomers rewriting physics textbooks. How could a single star defy the theoretical upper limit of stellar mass? The answer, as it turned out, wasn't a cosmic anomaly, it was a cosmic illusion. High-resolution imaging exposed Pisces 24-1 not as one star, but two brilliant siblings orbiting so closely that even the best ground-based telescopes had been fooled for decades. The discovery sent shockwaves through astrophysics. Side-by-side comparisons of pre- and post-Hubble images tell the story. An amorphous blob of light in early photographs resolved into twin points by Hubble's razor-sharp optics. The transformation wasn't just technical, it was philosophical. Suddenly, the record books needed revising, and the theoretical ceiling for star masses snapped back to reality. The siblings, while still impressive at roughly 100 solar masses each, no longer threatened the laws of physics. What seemed like a universe-breaking outlier became a lesson in the limits of human observation. This cosmic case of mistaken identity reveals how technology shapes our understanding of the cosmos. Early spectrographic analyses of Pismis 24.1 light hinted at something unusual. The composite spectrum showed conflicting features that suggested rapid rotation or bizarre atmospheric dynamics. Only when Hubble's wide-field camera separated the overlapping light waves could astronomers untangle the signatures of two distinct stars. The revelation echoed across astronomy. How many other single stars hiding in plain sight were actually multiples? The Pismis 24 cluster itself adds another layer of intrigue. Nestled within the emission nebula NGC 6357, often called the Lobster Nebula for its pincer-like dust lanes, this stellar nursery hosts several other massive stars. Infrared observations show how Pismis 24.1 ultraviolet Fury sculpts the surrounding gas, creating towering pillars where new stars are forming under the pressure of its radiation. Even demoted, this binary system remains a dominant force in its neighborhood, proving that cosmic significance isn't just about records, it's about impact. Beyond the science, Pismis 24.1 story humbles us. Every technological leap from Galileo's primitive telescope to Hubble's orbiting eye reshapes our cosmic perspective. What we know today might be tomorrow's footnote as instruments peel back layers of cosmic deception. The universe, it seems, delights in keeping its greatest secrets just beyond the edge of our current vision, waiting for the next generation of stargazers to look closer and see deeper. VY 83 in M33 isn't just another star. It's a cosmic yardstick, a beacon so luminous it helps measure the universe itself. Nestled within the Triangulum Galaxy, a swirling pinwheel of stars and gas nearly 3 million light-years from Earth, this luminous blue variable burns with the intensity of 3 million suns. While most stars on this list call the Milky Way home, VY 83 extragalactic address makes it special. Its light, captured by telescopes like Hubble and James Webb, doesn't just reveal the life cycle of massive stars, it holds the key to calculating distances across the vast intergalactic void. Finding VY 83 in deep space images feels like spotting a single firefly in a glittering cityscape. The Triangulum Galaxy sprawls across hundreds of thousands of light-years, its spiral arms dotted with star clusters and glowing nebulae. But zoom in, and VY 83 stands out, a brilliant blue-white pinpoint flanked by the telltale haze of ejected material. Its location along one of M33's outer arms provides a pristine backdrop, free from the dust and crowding that complicate observations in our own galaxy's core. This clarity is priceless. Unlike Milky Way stars whose distances we triangulate using parallax, extragalactic stars like VY 83 require cleverer tricks, and that's where its variability becomes invaluable. As a luminous blue variable, VY 83 pulses unpredictably, its brightness swinging wildly as it teeters on the edge of stability. These fluctuations might seem chaotic, but they follow a hidden rhythm tied to the star's intrinsic luminosity. By comparing its apparent brightness, how dim it looks from Earth, to its known absolute brightness, how much energy it actually emits, astronomers apply the distance modulus, a cosmic version of judging how far away a light bulb is based on how faint it appears. The math is straightforward, but the implications are profound. VY 83 becomes a stepping stone in the cosmic distance ladder, a sequence of methods that let us leap from measuring nearby stars to gauging the scale of the entire observable universe. The James Webb Space Telescope's infrared eyes reveal even more. VY 83 surroundings shimmer with heated dust, sculpted by the star's violent winds into intricate loops and filaments. Spectroscopy uncovers the fingerprints of heavy elements like oxygen and nitrogen in these ejecta, ash from the star's internal fusion furnaces. These elements will eventually seed future generations of stars and planets, making VY 83 not just a measuring stick but a chemical factory. Yet the real magic lies in collaboration. VY 83 isn't studied alone, it's part of a celestial ensemble. By comparing it to similar variables in the Milky Way and other galaxies, astronomers fine-tune their distance calculations, cross-checking methods to minimize errors. Each observation tightens the cosmic tape measure, letting us map the universe's expansion with growing precision. In this grand endeavor, a single star's tantrums become data points that echo across the cosmos, helping answer the biggest question of all: how vast exactly is our universe? S Doradus doesn't just vary, it reinvents itself. As the original luminous blue variable, this star wrote the playbook for stellar volatility. Its spectacular moods swing so extreme they became the gold standard for an entire class of cosmic divas. Nestled in the Large Magellanic Cloud, 169,000 light-years from Earth, S Doradus alternates between two dramatic personas: years of quiet simmering as a hot blue supergiant, punctuated by violent outbursts where it swells into a cooler, crimson behemoth. During these eruptions, its radius balloons to nearly 100 times its original size, enough to swallow the orbit of Venus if placed in our solar system, while its outer layers grow so diffused they resemble the wispy edge of a candle flame. The star's greatest spectacle unfolded in the 1920s, when it brightened to rival the entire Tarantula Nebula surrounding it. Archival photographs from that era show S Doradus flaring like a cosmic supernova, its light echoing across the decades as proof of nature's capacity for celestial theatrics. Unlike ordinary variable stars that flicker modestly, this LBV's luminosity swings by a factor of 10, equivalent to swapping a 100-watt bulb for a 1,000-watt floodlight without warning. Modern spectroscopy reveals why S Doradus isn't just shedding surface material. It's ejecting entire chunks of its atmosphere in spasms of self-destruction, creating a glowing shroud of ejected gas that alternately masks and magnifies its brilliance. Centuries of observations tell a story of runaway instability. 18th century star catalogues logged it as a nondescript point, while 19th century astronomers noted its peculiar color shifts. By the 20th century, the truth emerged: this was no ordinary star but a laboratory for extreme physics. Hubble's snapshots capture the aftermath of its tantrums, vast arcs of debris expanding at speeds that would cross the continental United States in seconds, their intricate braids and loops sculpted by magnetic fields stronger than any found on Earth. The real fascination lies in S Doradus's stubborn refusal to explode. Most LBVs flirt with catastrophe before detonating as supernova, yet this star has weathered countless eruptions over millennia. Some theorists suggest it's cheating death through sheer mass so gravitationally powerful that even its violent ejections can't trigger collapse. Others argue we're witnessing a slow-motion implosion, where the star sheds just enough material to stave off disaster while inching toward an inevitable finale. One thing's certain: S Doradus's light, arriving today, began its journey when human ancestors first crossed land bridges into new continents. By now, this cosmic chameleon may have already met its fate, leaving behind not just a legacy of light, but a blueprint for understanding how the universe's most tempestuous stars walk the tightrope between brilliance and oblivion. Sure 25 isn't waiting for permission to die, it's already dressing for its funeral. This blue supergiant, lurking in the sprawling star cluster NGC 3006, 20,000 light-years away, wears its fate like a crown, a perfect glowing ring of nitrogen-rich gas floating serenely around its equator. The resemblance to SN 1987, the most studied supernova in modern history, is uncanny. Just like its infamous predecessor, Schrödinger 25 ring wasn't sculpted by gentle stellar winds but by violent convulsions in its final chapters, a cosmic cry for help written in atomic elements. Hubble's ultraviolet images capture the eerie symmetry of this structure, a fluorescent halo 2 light-years wide, pulsing with the energy of a star rehearsing its own destruction. Place Hubble photos of Schrödinger 25 and pre-explosion 1987 side by side, and the parallels become spine-tingling. Both stars are blue supergiants of nearly identical mass, around 18 times heavier than the Sun. Both sport bizarre chemical abundances, with surface layers stripped away to reveal helium and nitrogen fusion byproducts. Most tellingly, both are wrapped in those enigmatic rings, celestial bullseyes that mark ground zero for future supernova. For 1987A, the ring became a spotlight when the star exploded, fluorescing brightly as the shockwave slammed into it. Schrödinger 25 ring now glows with that same ominous potential, backlit by the star's ultraviolet fury like a neon sign reading "Next." Yet Schrödinger 25 isn't just a carbon copy, it's an upgrade. While 1987A's ring was relatively simple, Schrödinger 25 nebula shows intricate braiding and knots, visible in polarized light studies that reveal magnetic fields weaving through the gas like invisible threads. Spectroscopy uncovers even stranger details. The ring isn't purely nitrogen but laced with neon and sulfur, elements normally buried deep in a star's core. Their presence suggests Schrödinger 25 has suffered apocalyptic belches, violent eruptions that dredged up material from near its heart and blasted it into space. This isn't just a star preparing to die, it's unraveling from the inside out. The countdown hinges on two numbers: Schrödinger 25 temperature, holding steady at 18,000 Kelvin, and its luminosity, flickering at 200,000 times the Sun's output. Both are textbook signatures of a star fusing elements far heavier than hydrogen in its core, a ticking clock that could expire tomorrow or in 100,000 years. When collapse comes, the explosion will be spectacular. Supernova models suggest its ring will light up like a cosmic donut, fluorescing as the shockwave ionizes the gas. The event might even outshine its host cluster temporarily, casting shadows on any hypothetical planets within 1,000 light-years. But Schrödinger 25's greatest value lies in its rarity. For every million stars, perhaps one matches this precise configuration, a blue supergiant caught in the act of weaving its own funeral shroud. Every new observation peels back another layer, offering clues about how massive stars broadcast their impending doom. Some theorists argue the ring is evidence of a swallowed binary companion, its material smeared into a disk during the cosmic cannibalism. Others see the aftermath of a near supernova collapse that somehow aborted, leaving the star teetering on the edge. Whatever the truth, Schrödinger 25 stands as a monument to stellar mortality, a reminder that even the universe's brightest lights are just temporary sparks against the dark. Betelgeuse isn't just another twinkling dot in Orion's shoulder. It's a ticking time bomb wearing a cosmic disguise. Even through small backyard telescopes, this ruddy giant pulses like a slow-motion strobe light, its surface simmering at a relatively cool 3,600 Kelvin. But in late 2019, something extraordinary happened. Betelgeuse's light dipped to its faintest level in over a century, dimming by nearly 2/3 before mysteriously brightening again. Amateur astronomers worldwide caught the transformation in real-time time-lapse sequences compiled from garden observatories, show the star shrinking from its usual top 10 brightness to barely making the top 20, a change visible even to the naked eye under dark skies. This wasn't just random flickering. High-resolution images from the Very Large Telescope revealed the culprit, a titanic dust cloud spewed from Betelgeuse's southern hemisphere, blocking our view like smoke across a spotlight. The star's supergiant status means its outer layers cling as loosely as cobwebs, allowing convection cells larger than our solar system to belch gas and dust into space with ease. Spectroscopy during the dimming event uncovered another clue: the star's temperature barely changed, proving the dimming came from obscuration rather than some internal collapse. Those backyard observations suddenly became critical data points, helping professional astronomers separate fact from speculation about this premature supernova scare. What makes Betelgeuse particularly fascinating is its accessibility. Unlike most stellar behemoths hidden in galactic backwaters, this one lies a mere 700 light-years away, close enough that Hubble can resolve surface features resembling glowing archipelagos on a simmering Red Sea. Its angular diameter spans about 50 milliarcseconds, a measurement amateur radio astronomers can verify using interferometry techniques with surprisingly modest equipment. Citizen science projects like the American Association of Variable Star Observers have tracked Betelgeuse's rhythms for decades, compiling light curves that reveal not just its roughly 400-day pulse cycle, but also shorter, erratic fluctuations hinting at deeper turmoil. The star's ultimate fate is written in these tantrums. Core models suggest Betelgeuse has already fused silicon into iron, the death knell for any star. When gravity finally overcomes the last whispers of nuclear fusion, the collapse will trigger a supernova visible in broad daylight, potentially outshining the moon for weeks. What seems like a distant inevitability on human timescales is for Betelgeuse a countdown measured in millennia, or perhaps much sooner. For now, it remains both laboratory and teacher, proving that even the most familiar stars can still spring cosmic surprises. Every snapshot from a hobbyist's telescope, every spectral reading from a university observatory, adds another piece to the puzzle of how these titanic stars spend their final, furious years. And when Betelgeuse does finally explode, it won't just be the end of a star. It'll be a once-in-a-millennium astronomy lesson written in light bright enough for everyone on Earth to read. These stellar titans scattered across the cosmic tapestry might seem like alien monsters compared to our modest sun. Yet every violent eruption, every pulse of radiation, every swirling stellar wind holds clues to the forces that shape even our own solar companion. The same nuclear furnaces that power hypergiants burn in our sun's core, just on a gentler scale. The magnetic storms that ravage distant Wolf-Rayet stars mirror the quieter flares that dance across our sun's surface. Even Betelgeuse's dramatic dimming echoes the subtle brightness shifts our sun undergoes over centuries. These extreme stars aren't just cosmic oddities, they're mirrors held up to nature's laboratory, showing us what happens when stellar processes get cranked to 11. Yet for all we've learned, these giants guard their secrets fiercely. We still don't fully understand why some stars balloon into unstable behemoths while others remain relatively compact. The precise triggers for hypergiant eruptions like Eta Carinae's 19th century outburst remain hotly debated. Even basic questions like the upper limit for how massive a star can form keep astronomers revising their textbooks. Every time we point new telescopes at these objects, whether it's Hubble catching Betelgeuse's dust clouds or James Webb dissecting the Pistol Star's nebula, we uncover fresh mysteries that rewrite our models. Here's the wonderful paradox: these stars feel impossibly distant, yet you can connect with them tonight. Step outside and let your gaze drift to Orion's shoulder. That fiery gem is Betelgeuse, a star whose light left during the European Renaissance. Train binoculars on Scorpius to spot Antares, a red supergiant so vast its atmosphere froths like a boiling cauldron. Even without equipment, the summer Milky Way arcs overhead like a bridge to these cosmic powerhouses, each twinkle a potential hypergiant too far away to resolve. This isn't just stargazing, it's time travel. The photons hitting your retina spent centuries or millennia racing through the void, carrying stories of stellar furnaces that predate human civilization. Next time we'll explore what happens when these titans finally meet their explosive ends, from supernova that outshine galaxies to the bizarre black holes they leave behind. Until then, remember, when you look up, you're not just seeing points of light. You're witnessing the universe's most extreme physics experiments blazing defiantly against the dark.